This is gas stoichiometry, module 7.01. And what we're going to be looking at is converting between the mole and the volume of a gas, specifically at standard temperature and pressure. We have learned previously to convert between the mole and a certain number of particles. So, for example, the particles that we look at are atoms, molecules, or formula units if we are talking about ionic compounds. However, since everything that we're talking about today is going to be in the gas phase, all we're going to worry about is atoms and molecules because we're not going to worry about ionic compounds. You also learned earlier how to determine molar mass using the periodic table. So previously you were going back and forth between mass, the mole, and particles, always going through the mole and using dimensional analysis. What we are going to add today is also being able to add volume, and it's particularly volume of a gas. To do this, we're going to look at Avogadro's hypothesis. Avogadro said that equal volumes of gas at the same temperature and pressure contain an equal number of gas particles, and these are going to be atoms or molecules. So let's choose a temperature, 0 degrees Celsius, and exactly 1 atmosphere. This is called STP, standard temperature and pressure. Our first balloon has 1 mole of helium. It has a volume of 22.4 liters and contains 6.022 times 10 to the 23rd atoms. The mass of the helium is 4.003 grams from the periodic table. The balloon to the right contains oxygen, exactly 1 mole. It also has a volume of 22.4 liters. It contains 6.022 times 10 to the 23rd molecules, but the mass is 32 grams. Remember, we take 2 times 16.00 grams, and that is 32.00 grams. So the molar volume is the volume of exactly 1 mole of gas at standard temperature and pressure. Standard temperature and pressure is 1 atmosphere and 0 degrees Celsius. This is something you need to memorize. So now we've got a new conversion factor. We know that 1 mole of gas equals 22.4 liters at STP for any gas. This means that now we know that 1 mole is 6.022 times 10 to the 23rd particles. We can look at the periodic table for the molar mass, and we can use our new conversion, 22.4 liters per mole. So let's work through a few examples. A neon light contains, neon's a noble gas, 0.51 liters of neon gas at STP. How many moles does the light contain? So our given is 0.51 liters of neon, and we are trying to find moles of neon. So we set up our dimensional analysis, 0.51 liters of neon. Remember, in dimensional analysis, we always bring our units down. So we're going to bring down liters of neon. And if we look here, up here, we can go, oh, if I have 1 mole of neon, I have 22.4 liters. Remember, in our calculator, we would plug this in as 0.51 divided by 22.4. And this is equal to 0.00, 0.023. Let me fix that. .023 moles of neon. Now up here, I have written the answer as 2.3 times 10 to the negative second mole. All this is done is put it in scientific notation. Okay, let's do another example, and then you are going to try 2 problems. A helium balloon contains 0.325 moles of gas at STP. What is the balloon's volume in liters? Remember that STP means 0 degrees Celsius and exactly 1 atmosphere, abbreviated ATM. So we start with the 0.325 moles. And in this case, it's a gas. We don't specify which gas. Doesn't matter, because we know that 1 mole of gas has a volume of 22.4 liters of gas at STP. We do our math and we get 7.28 liters of helium. Well, actually, look, there I said it was helium, but it would hold true if it was any gas. All right, you are going to try the problems in red. I'll leave the sample problem displayed up there for your reference. So I'm going to pause and you're going to try these problems. Here is the setup that you should have had for number 3. Now, the question came up, how do I enter this in my calculator? So let me do a little review on how to do scientific notation in your calculator. So this is for the TI-30XS or a graphing calculator. So you should enter 5.5. Then you're going to push the second button, then the EE key. And then you're going to enter the 5. Then divided and 22.4. So remember that second EE combination means times 10. And let me highlight that in yellow to help you remember it. So second EE means times 10 raised to some power. And so the 5 is the power. All right, since we've straightened that out, I want you guys to try numbers 4 and 5. Here are your answers for 4 and 5. Remember that each time your units need to cancel as you go down. Let's draw the units canceling so that you can see that we've canceled liters, okay? Number 5, we've also canceled liters of chlorine going down. The next 2 problems, we're going to ramp things up a little bit. What we're going to do is go between grams and volume. So a balloon contains 1.2 grams of helium. What is the balloon's volume at STP? So our given is 1.2 grams of helium. Our find is liters of helium. So we start with 1.2 grams of helium. We have to do unit cancellation or dimensional analysis. So grams of helium comes down, and we're going to convert that to 1 mole of helium. This means that we need to look at the periodic table. And just in case you didn't have that in front of you, helium is element number 2, so it has 2 protons, and its molar mass is 4.003. So we write 4.003. Now, we're not to liters yet, so now we've got to cancel out the moles of helium, and we are going to go to liters of helium. So we have 22.4 liters of helium in 1 mole of helium. We do the math and we should get 6.7 liters of helium. Now, in terms of how you plug this into your calculator, you would plug in 1.2 times 1 times 22.4, everything on the top. Make sure you use parentheses, and then divided by 4.003 times 1 to get the answer. Now, anytime you have ones, you can omit it, but I wanted to show the ones there so that you understand the logic. Everything across the top in parentheses divided by everything across the bottom in parentheses. Let's take a look at a second one. how many grams of fluorine gas are in a 38.2 liter container at 0 degrees Celsius and 1 atmosphere. So this time we're starting off with 38.2 liters. And it's fluorine gas. That's a diatomic, something you need to remember. Let me write the element symbol for fluorine, or the element number. We have 19.00, and fluorine is element number 9. It has 9 protons. Okay, we're going to bring down liters of fluorine and convert that to moles of fluorine. But we don't want to stop at fluorine. We are trying to get to grams. So 1 mole of fluorine has a mass of 32.00 grams of fluorine. Let's look at how all our units were canceling out. Liters of fluorine, moles of fluorine, moles of fluorine. And we're left with what we were looking for. We should have 3 significant figures based on the 38.2 liters. So we have 64.8 grams. Let's do one more example. So we've gone from liters to grams. The last one I want to look at is how many molecules of N2 are in 43 liters of N2. So that should be a subscript, and it's not. So our given is 43 liters of nitrogen, and we are trying to find molecules of nitrogen. So we start with our 43 liters of nitrogen. We're going to bring liters of nitrogen down. We always go through the moles. So 22.4 liters is the volume of 1 mole of nitrogen. We're going to bring 1 mole of nitrogen down, and we're going to go to molecules. And we go, oh yeah, you know what? I need to remember that 1 mole equals 6.022 times 10 to the 23rd things. So I'm going to write 6.022 times 10 to the 23rd molecules of N2. And plug everything into the calculator. Your calculator says 1.56 times 10 to the 24th, but we can only have 2 significant figures, so you should write 1.6 times 10 to the 24th. Let's go over how to enter this in your calculator. So you would enter in your calculator 43 times 1 times 6.022, second button, EE button. Then you'd enter 23. All of this has got to be in parentheses. Then you're going to divide it by 22.4, and you could or could not multiply it by 1. It will give you the same answer. Okay, so a lot of this should have looked very familiar. All we did is add that 1 mole equals 22.4 liters at 0 degrees Celsius and 1 atmosphere.